So last time, if you remember, I discussed with you, well, last two times, better to say, we discussed the general position theorem, third theorem. The proof is contained in the appendix to my lectures. It is my notes. It is very clear. I will not discuss it here. And as the first application, we proved the embedding theorems. We proved them in the compact case. You can think how to generalize it to general case and non-compact case. And the theorem says in its ultimate statement that every n-dimensional manifold can be embedded into R2n plus 1. And moreover, any smooth map of a manifold into a space of dimension 2n plus 1 or more can be approximated, C infinity can be approximated by embeddings. If you replace the word embedding by the word immersion, then the same is true, but you will have to, you can change the dimension 2n plus 1 to the dimension 2n. Also, I said, if you remember, that there are other embedding theorems. In particular, it is still true that any n-dimensional manifold is embeddable into R2n. Only the approximation part should be excluded. That doesn't work in this dimension. And in many cases, there exists a possibility of further reducing the dimensions. It is known, however, that in many important cases, this reducing is not radical. For example, it is true, I didn't say this last time, but you may be interested, that if you have, if you consider just RPn, and you denote as D of n the minimal dimension of Euclidean space into which it can be embedded, then the difference between 2n and D of n can be estimated as a logarithmic function. So not too much. And the same is true for complex projective spaces in many other cases. So actually, for, I don't know how to formulate it, but the general feeling is that you can consider a sort of arbitrary, randomly chosen n-dimensional manifold, then it is embeddable in R2n, maybe slightly less, but generically this slightly means something logarithmic. Such a theorem certainly doesn't exist, but sort of expectable. I want to mention, speaking of the third theorem, you remember third theorem. It says that for an arbitrary smooth map, well, C infinity map between two manifolds, the set of critical value, not critical points, is thin in different senses. There are two most common statements: that it has measure 0, or that it is countable intersection of nowhere dense closed sets. This is a possible statement. This is a possible statement. And there are other statements. Actually, especially in the 60s, many other general position theorems were formulated and proved by different people. I think that the place where we're going to find so much about this that you will really hate the subject is the book written by Abraham. I remember on the initial R. Abraham. He himself, Abraham himself, proved the most general position theorem, which certainly will not formulate. But there is one theorem which I want to mention, although not to prove. It can be deduced from the third theorem without much, third theorem plus the partition of unity notion, which it can be proven, and it is sort of important, unlike many other general position theorems. It belongs to René Thom. Have I ever heard this name? In conjunction with what? Thom spaces, yes, I know Thom spaces. I understand. Normally, people know Thom by maybe the reason of, because his, I think, least important of his wonderful topological works is very popular. It is about the so-called theory of catastrophe theory. People like, there are many popular books about this, and this theory is generally attributed to René Thom and also Zeeman, such British mathematician. Actually, neither of them were the true authors of this theory, which belongs to the same person, actually, whom we discussed here many times, Huster Whitney, really wonderful American topologist who did lots of things. Yes, so I will formulate a general position theorem belonging to Thom. Just formulate. Suppose that we have the following things. Suppose that we have a manifolds M and N, and a submanifold as manifolds, and a submanifold, say V in N. Then a map F, smooth map M into N, is called transversely regular. People usually say T-regular. With respect to W, to V, excuse me. If for every point P in M, say that f of P belongs to V, the map T, the image of the map D, P, F of T, P, M, it certainly belongs to T f of P N, but the condition is condition of T regularity that the sum dpf tp m plus T f of P V is the whole space T f of P N. You understand, if this is T f of P N, this is 0, this is T f of P V, then the image of TPM covers the transverse direction to TPV. No, this is not necessarily direct sum. It may be more. These two spaces may have intersection, not zero dimensional. This picture is two dimensional, so I don't have much opportunity. But these two spaces, this one tangent to V, and this the image of the map. So the picture, if this is N and this is V, then the image of M should be transverse to V. The dimensions of V and N together not necessarily give the dimension of V and M. Maybe the sum of them may be more than the dimension of N. So the intersection is not necessarily zero dimensional. But the transversality holds. It is the definition. And the theorem, Tom theorem, says, again, many different statements, but the most important statement, that every smooth map can be in the C-infinity sense, approximated by T-regular maps. So you understand, if our initial map, so this is V, this is F of M, and they're not transverse. Then we can slightly deform F, and the map becomes transverse to V. This is the statement. Is it clear? And it is stronger. It is even not stronger. It is different from the Sard theorem, but certainly follows from it. Actually, in reality, all theorems, all generalization theorems which exist in topology, and the book of Abraham actually creates also this impression. All the theorems ultimately follow from the Sard theorem, which is sort of elementary, but gives the right condition, right statement about maps. After it, using it, you can do a lot of things. This is all I wanted to say about general position theorems, maybe even more than I should have said. Questions about this? Henry, you, yes, you.
So the theorem itself is that with measure, like if you choose a random map with measure 1, it'll be transverse like that? Or?
You choose a random map, a random smooth map, and then approximate it with a random map is not irregular. Look at that picture on the right. A regular map is not. If you have a submanifold and then a map of some other manifold, then this map is not transverse to the manifold. But they make it transverse by, well, small deformation in the C-infinity sense. No questions about these questions? Henry, you owe me 100 questions. So if you ask a question, you will still owe 99. No? Yes. Well, this subject is interesting, and embedding theorems, actually, which I mentioned, also give some, create some very interesting chapter in topology. I'm sort of disappointed that, again, I need to speak about things not so exciting. Up to this moment, we considered manifolds. And the manifold has definition and so on and so on. But theory of manifolds cannot survive without a more general notion. This is a manifold with boundary. People also say D manifolds, using for D the symbol for partial derivatives. So a manifold with boundary. is a generalization. A D-manifold is a generalization of a manifold, but gives some new examples. So let me give the definition. Definition is the same as the definition of manifold with one change. Namely, we consider again the set M and charts U, phi. U, however, will not be an open set in Rn. U is an open set in a space which you denote as Rn minus. And Rn minus is just this part of Rn for which the last coordinate is non-positive. Certainly, well, we are not in a position to discuss definitions, but still, if we do, you can ask why we take last coordinates and why non-positive. And my answer is very simple, more convenient. Certainly, you can create the same theory, defining Rn minus, for example, as the set of points where x1 is non-negative. But this will lead to actually appearing some undesirable negative ones at different powers. So this definition is actually the most convenient, although there are other equivalent definitions possible. So you understand this. A manifold with boundary and dimensional. All the rest of the definition, compatibility of charts and so on and so on, is absolutely the same as for theory of manifolds. Actually, we can an open set in Rn minus may be also an open set in Rn if it doesn't touch the boundary hyperplane. So it is very possible that a D-manifold with boundary is actually a manifold in our previous sense. The most visible example, take the disk with boundary, closed disk. It's a manifold with boundary. A point here have a chart like this around. A point here has a chart like this. Right? For the boundary charts, the last coordinate is always non-positive, less than or equal to 0. x2 in this case. This, I hope, clarifies the definition and also shows that we have new examples. This is disks of any dimensions, Dn. There are other examples. They will appear, but you will see them. If we have a manifold with boundary, then there are two manifolds without boundary. When I say manifold without boundary, I mean manifold in my previous definition, or also a D-manifold points whose points have this have charts with the domains open sets in Rn, not in Rn minus. Open in Rn. They should be subsets of Rn minus, but they can be still open in Rn if they do not touch the hyperplane. Now, so when I say manifold without boundary, I mean again D-manifold simply without charts which touch the boundary part of Rn minus. Now there are two manifolds. Let me say first a point P. So let M be a D-manifold. A point P in M is an interior point. Interior point. If there exists a chart U phi such that U is open in Rn. In the disk, the points of the interior, yes, interior, are interior points of this disk, obviously. Now, it is very clear that interior points compose a manifold with the same charts, right? So if M is a D-manifold, then there arises M a D-manifold interior M, a manifold of the same dimension. The interior part of the D-manifold. What about the complement? It is denoted as dm. What do you think of that? It is an n-1 dimensional manifold, which we can easily see. I will say something about this. Does it have boundary? Unlikely. So dm is an if M is an n-dimensional D-manifold, then dm so this is n-dimensional is an n-1 dimensional manifold. How to explain this? Well, sort of obvious, but still. What is a point in dm? Very obvious. It is a point for which there is a chart U phi of M such that P belongs to phi of U intersection Rn minus 1. Right? Next, I can consider all such charts and restrict them to phi inverse Rn minus 1 phi, and this will be a chart of dm, obviously. This gives you an atlas on dm and shows that dm is a manifold. Now here the domains of the charts are open sets in Rn minus 1. So this is a manifold without boundary. With empty boundary, a manifold without, in our previous sense, however you want to express this. Is there? There is one thing. Certainly, I could try to hide it from you, And maybe you would not notice, although who knows. But actually, here I miss some important thing. Let me mention it. You remember there was an example of the disk. I don't want to draw it again. Are you sure that points of the boundary, points on the circle, are not interior points? To be sure of that, basically we need to know that a point on the boundary of the disk doesn't have a neighborhood, which is homeomorphic, diffeomorphic to an open set in the plane. And you do not need to speak of R2. I said homeomorphic or diffeomorphic. With homeomorphism, actually, this is quite a theorem. There is the following result in topology, which I don't want to touch here, the more so that it requires maybe not very deep, but still algebraic topology to prove it. If we have a subset of Rn, listen to me, have a subset of Rn, which is homeomorphic to some open set of Rn. Okay? Then it is open itself. Do you understand? You have a subset in Rn, maybe in R2. And what I know that it is, I don't know anything about this, but only one thing, there is a homeomorphism between this subset and an open set in R2. And they say that this subset is also open. Can you prove this? How to prove this? It is necessary, because if it is not so, then actually it is very easy to prove. Then every D manifold, for every D manifold, absolutely all points are interior. But again, this theorem holds that if there are two theorems, homeomorphic, diffeomorphic. If a subset of Rn is homeomorphic to an open subset of Rn, then it is open itself. Then replace the word homeomorphic to the word diffeomorphic, and the same. To prove this for homeomorphisms, we actually need to use some algebraic topology. Probably it is not avoidable. We need to consider the local homology at points. This I address this to people who may understand the subject. But for diffeomorphisms, this follows from elementary analysis theorems. You can prove this easily from the inverse function theorem, and the proof is very direct. So in our theory of smooth manifolds, this is not a deep theorem. But for topological manifolds, it is not deep precisely, but still requires some work. Since I don't want to say anything else about this, your questions. You do today, asking you, Dale, asking questions. You do also.
I was just wondering about the homeomorphic proof, but I'll ask you to do that.
Do you know some algebraic topology?
Yeah.
Yes. Then consider a point and take local homology. That's homology of your set modulo the complement to this point. And if the set is open, then something is true about this homology. And this is sufficient to understand whether the set, you can formulate the fact that the set is open in terms of local homology, after which it becomes topologically invariant.
So basically non-trivial local homology groups implies...
Well, not just non-trivial. For an open set, local homology is predefined. We simply know them. Non-trivial in one dimension, in the upper dimension. Well, So let me still skip it. Now I want to skip not this, but I want to skip 2 miles of possible way. I want to say first, in very general and certainly not very sincere way, that whatever we said about manifolds can be repeated for d-manifolds. It is 99% true, but remaining 1% requires some work. So let us try to take this trail. Smooth maps. Smooth maps are defined for d-manifolds precisely as they are defined for manifolds, between d-manifolds. The only thing that sometimes it is reasonable to require that a smooth map takes boundary into boundary points into boundary points, which certainly doesn't follow from the usual definition. I prefer to have my general definition without this condition. If not, we can say that f takes fm into n takes dm into the image f of dm is a subset of dn. So no problems with that. Submanifolds. Here, actually, there are many possibilities of giving this definition. What is a submanifold of a d-manifold? I remember in this room, several weeks ago, we discussed the definition of a submanifold of a manifold, and I suggested several examples. And as far as I remember, actually, our thesis coincides. But still, how to define a submanifold of a d-manifold? Say, if we have a plane, this blackboard, and a very straight closed interval, you understand, on a line. We take a line on this plane and a closed interval. Does it deserve the name of a submanifold? This depends certainly on your attitude to the subject, but I prefer to give a definition in such a way that it is a submanifold. You remember when we defined submanifolds in the theory of manifolds, then actually everything was based on a pair, Rn, Rm. We consider charts in Rn, charts with the meaning Rn, and then the inverse image. The charts, the condition was that there are charts such that the inverse image of the submanifold charts in the neighborhood of points of this submanifold only. So we have a subset of a manifold. And for points of this subset, there should be special charts, very, very special charts. So that the inverse image of this set is the intersection of the domain of the chart with Rm. Here we need to do the same. Only the pair Rn, Rm should be somehow modified. We can consider again this pair. We consider this pair R m minus embedded in Rn. We can consider this pair. Well, it is better to draw it like this. Rm minus embedded in Rn minus. This is precisely what I want to use to define submanifolds. These three pairs. So a submanifold is defined precisely as it is defined for manifolds. But there is a possibility to replace Rn with Rn minus and Rm with Rm minus. And we consider these three possibilities. So for example, is the boundary a submanifold of a manifold with a boundary? Doesn't fit any of these three cases. This is not very convenient. Not very convenient. But still, this is what I'm going to consider. So this is my definition, and a manifold with boundary can be submanifold. Now, next thing, products. What do you think, my friends, of a product of two D-manifolds? Is it a D-manifold? You say yes. You're very optimistic, Virgil. Let me say, there is one yes which creates no doubts. A product of a manifold and a D-manifold is certainly a D-manifold. So, if M is a manifold and N is a D-manifold, then M cross N is a D-manifold, and D of M cross N is M cross Dn. Geometrically, it's so obvious that I don't think that it requires any comments. Right? But what if the both manifolds M and N are D-manifolds? Then, let me say, I prefer somehow to justify what Virgil says. Then, it may be regarded as a D-manifold, but still, but this requires some work. Maybe almost nothing, but still. Let's look at that. Manifolds, D-manifolds, you know. The best known D-manifold is a closed interval, right? Its boundary is a two-point manifold, right? What is the product of two closed intervals? And you say immediately, it is a square, if these intervals have the same length. It is a square. A square, if you imagine it, has some angular points. And it is not very much clear how to consider this as a smooth manifold. But it's not clear only at the first moment. So let M and N be D-manifold. Consider M cross N. Let P is a point in the M and Q is a point in the N. Then we have charts. U, phi, and V psi, and U is a map and open set. Actually, we can easily understand that U can be a map, phi can be a map of R M minus into M, the whole half space. And psi, so U is actually R M, and psi and V is R and minus. And together, they form a map. Phi cross psi, R M minus times R n minus into M cross N. It is the same as R m plus n minus. Definitely not the same. But what we can do, we can fix some correspondence between this, some homeomorphism between these two sets. Actually, there Rm minus is R1 times R1 minus, and Rn minus is R minus 1 times R1 minus. So to create a homeomorphism, fixed homeomorphism between this and this, is sufficient to describe a homomorphism R1 minus times R1 minus onto R2 minus. Let me draw the picture. This is R1 minus times R1 minus. This is R2 minus, right? It's very easy to define a homeomorphism which takes this into this into this, and that's all. Probably the best possible way is to introduce complex coordinates in the plane, and to say that it is z squared beta minus z squared, just to make it lower half plane. So there is a map which is very smooth everywhere, with the exception of the origin. And this is precisely what we use to identify R1 minus times R1 minus with R2 minus, and consequently Rm minus times Rn minus with Rm plus n minus. And as soon as we say this, our smooth d-manifolds can be, we can have products. And what is the boundary? So the product of two d-manifolds becomes a d-manifold. And what is this? Look at that. And you see it. This is dm times n plus m times dn. Very much usual product formula. It's not disjoint. The intersection is dm times dn. Is union. Union of two subsets. Not disjoint, no. Well, comments about this. So we consider products of d-manifolds as if it is a d-manifold with this boundary. Next problem. Probably I will not be able to say anything else, but this we will discuss, orientations. First, the notion of orientation is precisely as before. We can speak of oriented, orientable, whatever, orientations of d-manifolds. How to define an orientation of a d-manifold? There are different ways of doing that, but what do you prefer? For example, take the interior and simply say that an orientation of a d-manifold is an orientation of its interior. We can say, maybe less obliging, that actually d-manifolds, like manifolds, have charts. And charts create transition functions. the transition functions still have Jacobians. Jacobians should be positive. Then two charts are orientably compatible if the Jacobian of the transition function is positive. Yes. So what? I want to make statements, some statements, and you will estimate the level of triviality. First, if a D-manifold is orientable, then both interior and the boundary are orientable. Moreover, an orientation of the D-manifold gives rise to an orientation of both interior and the boundary. Certainly, it is very possible that a manifold is not orientable, but its boundary is orientable. Its interior will be not orientable also, but boundary may be empty. There is no more orientable manifold than the empty set. Yes. Can all this be regarded as obvious, trivial, and not deserving mentioning? If you say yes, then I partially agree. Still, there is some doubt. First, what if I say that I consider a D-manifold? I consider charts as they were defined. Okay? And then I say that I now so suppose that the manifold is orientable. So I have an atlas which possess the orientation. And yes, and even this creates a problem. Probably we will discuss next time, but now I have a question to you. Do you really think that the interval 0, 1 is orientable? You will think so. But what about our definition? This is the interval, okay? Consider a chart which covers this point. Consider a chart which covers this point. Do you really think that these two charts belong to the same orientation? No. No, because the coordinate is negative here, right? By this reason, we should be sort of cautious, but this is only in one-dimensional case. This is one thing. So speaking of orientations in dimension 1, very trivial case. We need simply to be cautious in our definitions. Now, when I say that if an orientation of a manifold gives rise to some orientation of the boundary, but if the manifold is one dimension, its boundary is 0 dimension. We never spoke of orientations of 0-dimensional manifolds. Yes.
Speak that half open interval or half closed interval is orientable.
You mean that this is possible to repair? I agree. But what is the orientation of the boundary? What is the orientation of the boundary of interval? 2 points. And here, actually, well, I wanted to finish, but you do not let me do this. So let me say, you may be surprised, but orientation of a 0-dimensional manifold, an orientation should be defined simply as a function which assigns to every component, every point, the sign plus or minus. As soon as we have this, certainly all 0-dimensional manifolds are orientable. And there are many orientations, 2 to the power n, when n is a number of components. As soon as we adopt this definition, everything becomes very clear. And if this is an oriented interval, that direction, then its boundary is plus this minus this. And everybody who ever heard of the fundamental theorem of calculus should know that. I finish now. Thank you for your attention.